Can you see the presentation?
Yes, let's start.
Okay, good afternoon. My name is Nicola. I'm a master's student at Bauman Moscow State Technical University, and the topic of my presentation is analysis of P300 features for target stimulus detection using artificial neural network with small dataset for BCI tasks. According to the World Health Organization, stroke is the third leading cause of death, with about 15 million strokes reported every year worldwide. Of these, 5 million die and another 5 million are left permanently disabled. Recovering from a stroke is a complex and long-term process. Medical rehabilitation is an important part of recovery and helps the patients to maintain and regain lost abilities. There are several methods for post-stroke rehabilitation, which is divided into high-tech methods, physiotherapy, and basic methods. In the past decade, many studies have focused on motor, cognitive, or speech recovery after stroke, where it was highly suggested to use brain-computer interfaces for post-stroke rehabilitation. Brain-computer interface is a technology that gives humans with motor disease the ability to directly control computers or any external devices using only brain signals such as EEG. One of the common used EEG patterns that used to design EEG-based BCI is P300. The P300 potential is characterized by a positive peak approximately 300 milliseconds post-stimulus, which is shown in figure 3. The main properties of P300 are waveform, amplitude, and latency. In figure 2, demonstrated a schematic of principal BCI components. Just turn on the video. Mhm. One of the most steps in designing BCIs is classification, where is widely used machine learning methods like artificial neural networks. It's well known that artificial neural networks works good with big and high quality datasets. However, when dealing with BCIs based on P300, one of the most problems that we suffer from during EEG classification step is the lack of high quality data, which leads in to use a small dataset in most cases. Accordingly, our first objective was training and evaluating BCI model performance with small dataset. The other objectives are represented in this slide. Talking about equipment, the EEG data have been recorded using Neuron Spectrum 5. The equipment characteristics is shown in the right table. EEG was registered via EEG cap following the 1020 system. For the stimulation, we have used a photon stimulator divided by 9 equal cells in the form of 3 by 3 matrix with a light diode in each cell. Each participant was asked to concentrate on one cell during each experiment phase. This cell was divided as a target cell, therefore the other 8 cells were called non-target cells. The experiment paradigms used in our study are clearly represented in these tables. As you can see, in each experiment have been chosen different stimulation parameters like stimulation frequency, size of photic stimulation matrix size with visual and auditory stimuli. An artificial neural network was used as a classifier for P300, which has 2 inputs according to the number of chosen features, 2 hidden layers with 5 neurons, and 1 output, with an activation function ReLU. The ReLU layer defined by the following function. Before the classification process, data normalization from 0 to 1 was obtained using the following equation. Due to the importance of P300 waveform as a main P300 property, cross-correlation value between EEG signal and wavelet marlet has been considered as an additional feature for P300, as this value could give us information about the shape of P300 signal. Cross correlation has been estimated between P300 and wavelet Morlet because of their similarity in signal waveform. For wavelet Morlet generation in MATLAB 2016b was used the following function. For comparisons, the data were split according to the stimulation frequency. The diagram in figure 8 clearly shows the algorithm used for choosing wavelet Morlet parameters. In this table shown how the parameters have been varied. Let's get into some examples. In this example, shown the variation process for the experiment 1 with a stimulation frequency equal to 3 Hz. On the right graph, the y-axis indicates the maximum value of the cross-correlation function between the averaged P300 non-P300 response and the wavelet Marlet for each set of wavelet Marlet parameters, which indicated by axis x. As you can see, this graph appears to be divided into 10 parts. This is caused by the changes of the parameter n, which indicates the number of wavelet points. To determine the most appropriate wavelet Marlet parameters, the difference between the maximum value of the cross-correlation function with the averaged P300 response and the maximum value of the cross-correlation function with the averaged no P300 response was considered. As you can see in figure 9, where this value indicated by axis y. Several methods for validation were used for evaluating our model, like area under ROC curve, precision, recall, and accuracy value. In this picture below shown an example of P300 classification. Mhm. In this slide, the results of our study is represented. In the right table, shown the most convenient wavelet parameters, while in the left table, shown classification results using artificial neural networks, where was used different set of parameters, either amplitude and latency, or latency and correlation coefficient, or amplitude and correlation coefficient. As you can see, best results indicated by green color and worst results indicated by red color. Based on our results, it was observed that the highest classification results were obtained in the first and second experiments, as we got reasonable classification results using testing sets, especially at 3 Hz stimulation frequency. However, the value of recall was considered as one of the most valuable validation parameters, due to the importance of the positive class, which indicates target stimulus. The relatively high results in some experiments are probably associated with dataset size and data splitting method. Therefore, in the future, it's necessary to expand the dataset size and use other data splitting methods. Before I finish, I would like to leave you with the following conclusions. The P300 signal has a high sensitivity to correlation changes, as different recommended values for wavelet Marlet parameters were obtained, even with similar stimulation parameters, indicating that the wavelet parameters should be chosen individually for each participant. No direct link was found between wavelet parameters and stimulation frequency, while on the other hand, a considerable improvement in classification accuracy was achieved using the correlation function as a P300 feature. So that brings me to the end of my presentation. Thanks for listening. If you have any questions, I would be happy to answer them right now. Just a
Um,
minute to...
Thank you very much. We have a lot of time for discussion because we go faster than usual.
Okay.
I invited questions from our colleagues, and I ask you two questions. First, I see that your area under curve is very high. It's very strange for some approach. Do you check that you have no leakage of test data, train data to test data?
Actually, it's only high in some experiments, like in the first, as you see in the first and the second, while in other experiments it's a little bit low. And I think it's due to the problems that we have unbalanced classification problem. So we have a ratio is about 9 to 1 for each class. So the second class is 9 times more data than the first class. So I think the problem is associated with unbalanced classification.
Could you present confusion matrix in this case?
Confusion matrix. Actually, I didn't show the confusion matrix because precision and recall could give us information uh, rather than confusion matrix. But I could send it to you in
Okay,
email or something like that.
thank you. And I ask questions about why you choose neural networks, because you use only multi-layer perceptron at this classification is not optimal for any problems. In any works, there are a lot of works which compare neural networks, support vector machines, and extremely randomized forest for classification. And randomized forest in any case is better choose for classification problem than usual multi-layer perceptron. And you can use, for example, XGD booster or something for classification of usual vectors. From my point of view, it improve your work. Of course, I understand that
Actually,
you lose neural networks in your work, but really you can obtain much better precision with other methods.
I totally agree with this point. It's a really good point. Thanks for asking. Actually, we use artificial neural. We have a very simple classification problem. We have only two inputs, one output with two classes, and we have a very small amount of data. So we choose artificial neural networks like an initial variant, while in further studies, we would like to expand our data and use other methods like support vector machine and random forest as user suggested. So for sure, we would use it in further studies.
Okay, thank you very much.
Thanks a lot.
The next speaker is Boris Gurevich. The speaker has two sequential presentation. First, it's acoustic optic device application for